Have you ever tried to light up a tiny LED bulb with a battery? It is a classic first project for anyone curious about electronics. You take a shiny new light-emitting diode, or LED. You grab a fresh battery, maybe a common 9-volt battery. You carefully touch the LED's long leg to the positive terminal and the short leg to the negative terminal. For a brilliant, wonderful instant, the LED shines with an intense, beautiful light. It is brighter than you ever expected it to be. You feel a small jolt of success. The light is on. It is working. But then, just as quickly as it started, something goes wrong. The brilliant light might flicker once. It might even make a tiny, almost inaudible popping sound. Then, the light goes out completely, leaving you in the dark. You might notice a faint, acrid smell of burnt plastic. If you were to touch the tiny plastic bulb of the LED, you would find it is surprisingly hot. The LED has burned out. This is a very common problem, and it happens when you forget one small but very important component. This simple mistake is something many beginners make, but it has an easy fix. The culprit in this tiny electronic tragedy is an uncontrolled flow of electrical energy. To understand why your LED burned out, we need to talk about what an LED needs to work properly. An LED is a special kind of electronic part called a diode. Its main job is to let electricity flow through it in only one direction. When that current flows through, the LED produces light. Every LED is designed to turn on at a specific voltage. This is called its forward voltage. Think of it as a tiny toll booth for electricity. You need to pay the right toll, the forward voltage, for the gate to open and let the traffic, the current, flow through and produce light. The forward voltage changes depending on the color of the LED. Red, about 1.8 to 2.0 volts. Green, about 2.2 volts. Yellow, about 2.2 volts. Blue, usually between 3.0 and 3.4 volts. White, usually between 3.0 and 3.4 volts. This is a fixed property of the LED. It will always try to drop this voltage when on. It cannot change or adjust on its own, which is the key to our problem. Now let's look at the battery. Batteries provide a steady, constant voltage. A brand new 9-volt battery provides about 9 volts. When you connect a 2-volt red LED directly to this 9-volt battery, a serious mismatch occurs. The LED only needs 2 volts. The battery is supplying 9 volts. The extra 7 volts have to go somewhere. That excess becomes a powerful force, pushing enormous current through the unsuspecting LED. The LED has no internal way to stop the surge. This massive rush of current destroys the LED. The semiconductor heats up incredibly fast. The heat becomes so intense that it literally burns and it melts the tiny structures that produce the light. The result, the LED gets hot, it smells bad, and then stops working forever. It didn't fail from a defect. It failed from being pushed beyond limits. It needs a guardian to control the current, and that guardian is the resistor. So, how do we protect our LED? We use a resistor. A resistor's job is to resist the flow of current. It acts like a valve in a water pipe, restricting the flow to a safe and manageable level. To choose the right resistor, we use a fundamental law of electronics called Ohm's law. Ohm's law gives us a relationship between three things: voltage, V current, I resistance, R. The formula is V equals I times R. Let's use a clear example. Imagine we have our 9-volt battery, our red LED, which has a forward voltage of 2 volts. We need a safe current for the LED. For most small LEDs, 20 milliamperes, which is 0.02 amperes, is a good, safe choice. This will make the LED bright enough to see clearly without stressing it. Our goal is to find the right resistance, R, to limit the current to this safe level. First, we need to figure out how much extra voltage the resistor needs to handle. Subtract the LED's voltage from the battery's voltage. 9 volts minus 2 volts equals 7 volts. That 7 volts is what the resistor must drop. The resistor turns that extra electrical pressure into a tiny bit of heat. Use Ohm's law. R equals V divided by I. V is 7 volts. I is 0.02 amperes. R equals 7 divided by 0.02. That calculation gives 350 ohms. Resistors come in standard values, so you might not find a 350 ohm resistor. 330 ohms or 390 ohms. Choose 390 ohms to be safer. Section 4. The Fix in Action. A step-by-step guide. Now that we understand the problem and have calculated the solution, let's put it all together, and get practical. We will build the circuit safely. This step-by-step process will ensure your LED lights up and stays lit. For this safe demonstration, you will need your battery, your LED resistor, 390 ohm. This process is simple and will give you the confidence to build more circuits in the future. Remember to take your time and double-check each connection before you apply power to the circuit. First, identify the parts of your components. The battery has a positive plus and a negative minus terminal. Your LED has 2 legs, or leads. The longer lead is the positive side, called the anode. The shorter lead is the negative side, called the cathode. The resistor does not have a positive or negative side. It can be connected in either direction. This makes it a very forgiving component for beginners to use. Getting the LED's legs correct is the most important part of this step, as it will only work in one direction. Next, let's connect everything together. This is called building a series circuit, because all the components are connected one after another in a single loop. Start by connecting one lead of the resistor to the positive terminal of the 9-volt battery. You can use alligator clips or a breadboard for this. Now take the other lead of the resistor and connect it to the long positive leg, the anode, of the LED. This places the resistor between the battery's power source and the LED, where it can do its job of limiting the current. Finally, complete the circuit. Take the short negative leg, the cathode, of the LED and connect it directly to the negative terminal of the battery. The moment you make this final connection, the LED should light up with a steady, pleasing glow. It will not be intensely, blindingly bright like it was without the resistor. Instead, it will be at a perfect brightness, the level it was designed for. You can leave it on. Touch the LED and the resistor after a minute. They should be cool or only slightly warm, a clear sign that everything is operating safely and correctly. Section 5. A bright future. Safety and memory aids. You have successfully lit an LED the right way. By adding one simple resistor, you have tamed the flow of electricity and created a stable, long-lasting circuit. This principle of using resistors to control current is one of the most fundamental concepts in all of electronics. It applies not just to LEDs, but to countless other components that require a specific amount of current to operate safely and effectively. You now hold the key to preventing one of the most common beginner mistakes, ensuring your future projects are successful from the start. To help you remember these crucial steps, it is useful to have a simple mnemonic or memory aid. For remembering Ohm's law, think of the word VAR, pronounced like veer. This stands for voltage equals current times resistance, V equals I times R. It is a quick and easy way to recall the formula when you need to calculate a resistor value. Another simple phrase to keep in mind is, LEDs need a limit. This reminds you that an LED, by its nature, cannot limit current on its own and always needs an external component, like a resistor, to do that job for it. Building circuits is a fun and rewarding hobby, but it is always important to prioritize safety. While the low voltages from batteries used in these simple projects are generally safe, it is a good habit to be careful. Always double-check your connections before powering up a circuit. If a component ever gets very hot or starts to smell, disconnect the battery immediately. As you move on to more complex projects with higher voltages or wall power, this habit of caution will be incredibly important for keeping you and your equipment safe. So, the next time you see a tiny LED, you will know its secret. It is not just a source of light, it is a delicate device that needs protection. You know that its enemy is too much current, and its best friend is a humble resistor. By understanding the relationship between voltage, current, and resistance, you have taken a giant leap forward in your electronics journey. You have the knowledge to make things light up, not burn out. Keep experimenting, keep learning,